Hello, I am Uchio KONDO. I'm going to start about the story of Rucy. First, I'm going to introduce myself. I am Kondo Uchio. I worked at GMO Paper and live in Fukuoka. I was a RubyKaigi organizer in 2019. I like Ruby, MRuby, Rust, and Duolingo. So again, I'm going to about my program, Rucy, but before we can discuss on Rucy, there are a lot of prerequisites that need to be understood. So first, I'm going to talk about BPF. What is BPF? BPF, in simple words, is one of the latest Linux sorters. It is often confused because it is used for various purposes, but basically, it is a technology that allows users code to run faster and safer in the kernel. BPF is used, for example, in the following areas: networking. As the name BPF, Berkeley packet filter implies, BPF historically started with packet filters such as TCP dump, and it has been developed to run faster. Next one is server tracing, in other words, observability. You can aggregate kernel events more precisely than the classic solutions such as SAR, VMstat, S3, or perf. If you are running FreeBSD or Solidus, you are probably a fan of dtrace. It's been a dream come true for Linux users, but now with BPF, it's becoming a reality. You can also use BPF as a mechanism to filter what devices are allowed to access from inside the container. This is about the use case of device. The entire BPF program works as shown in the figure. This is about the use case of observability. This is about the use case of device access control from containers. BPF program will be loaded into kernel space. When accessing to a device, the context such as device major or minor codes are passed to BPF program, and then BPF will execute filtering. The point is that there is a BPF binary part that runs in the kernel, and the user space part to pass parameters from user space into the kernel and to get aggregate data from the kernel. So continue talking. Next topic is about whether you can use BPF from Ruby. The answer is yes. I started developing a project called RubyBCC in the middle of 2019. It allows Ruby to get access to BPF's observability features. RubyBCC is a Ruby binding of BCC. What the BCC is an SDK for developing tools for BPF. It's using Python and Lua. But I started developing RubyBCC because I was frustrated that BCC didn't support Ruby. Fortunately, BCC uses Python FFI. So in the same way, I used Ruby's fiddle to access the BCC. RubyCC is also one of the results of a Ruby Association Development Grant in 2019. However, there are some pitfalls with BCC. When running the trace using BCC, the compilation process of the BPF binary will be done. In other words, BCC does JIT compile. This causes some problems. First of all, the runtime overhead is a problem. Another is that you need LLVM, clang, and set up kernel headers for JIT compile. Try installing LLVM and clang from your Linux package manager. How big will it be? The size of the compilation environment can be a problem when you want to make a container image. Therefore, rather than using the JIT method like BCC, Linux community recommends to pre-compile the BPF binary. Incorporate it into the user space program. Install the whole stuff as a single file. Rather than continue to use BCC, I decided to develop a new tool. MRB seems to be the best way to achieve the one binary goal, but the problem here is the BPF binary, which can only be created in C effectively. We need to pass the C code to the clang command with target the BPF option as the slide shows. Since you are a Rubyist, you may be good at C language, but I decided to make a tool that enables Rubyist to make BPF binaries without writing any C code. This slide is a summary so far. Anyway, you need to write C language for the BPF binary. But I'm trying to make it possible to write every part of the BPF program in Ruby, only with a Rucy. So now it's time to talk about the technology behind Rucy. Rucy is a Ruby compiler to BPF target. In other words, Rucy will generate BPF program binary directly from a plain old Ruby script. And this is architecture overview. The process of compiling Ruby into a BPF program in Rucy. First, put your Ruby program into the Ruby parser. Then you can get the opcodes of mruby. Rucy internally interprets these mruby opcodes and extracts the necessary information for the BPF program. By doing so, we have the metadata and the binary representation of the BPF program. The object file of the object file of the BPF program should be in ELF format. As you have seen, I must talk about these opcodes, in other words, these binaries, in a little more detail. Let's start with the BPF opcode first. A BPF program runs on its own VM inside the kernel, which has its own instruction set. The VM can use 10 registers, and BPF instructions are basically 64-bit fixed. The layout looks like this. Instruction, destination register, source register, offset, and immediate value. An instruction consists of a combination of several bits. Here are examples of instruction combinations. I I'll explain MRuby's opcodes in the next session. Like CRuby, MRuby has its VM and opcodes, but the VM is a register machine. It can use 65,000 registers, but recommended to use only 256. Instructions in MRuby have variable lengths. For each instruction, the length depends on what kind of operand it will take. The size of the operand variables are 8 bits for B, 16 bits for S, 24 bits for W. If there is no operand, use Z. For example, op load I is an instruction to load a number into a register, and it takes BB operand. Then the all instruction is represented in 64 bytes. op jump if and op jump not takes a BS operand and represented in 32 bits. Now let's transpile MRuby's opcode into BPF's opcode. Here is a sample Ruby code. The method prog will be interpreted into MRuby opcodes like this. I try to figure out a way to make an equivalent assembly. The goal binary is like this. So first, let's ignore some instructions on the MRuby side that are not needed. Instructions like op load I can be converted directly into counterpart BPF instructions, as you can see in the slide. To change attributive method call to an object in MRuby to access to member of a structure in BPF, we use a combination of op move and op send. Now showing op move conversation rule. Processing of op send, the offset can be calculated from the receiver's variable name and call the method name. And the offset information is necessary to use the structure members in BPF. One more thing is that the strategy of jump instructions are quite different between BPF and MRuby. In BPF, just one instruction is used to determine jump, but in MRuby, 2 instructions are required. So in this example, OPEQ compares R3 with R4 and stores the resulting bool in R3. OP jump not will go to if R3 is false. To translate it as direct as possible, OPEQ is converted to ALU instruction with sub operation. The next line, op jump not judges that the value of Rx is not 0, and consequently judges that the 2 values do not match. Final one is op return. MRuby can return any register, but BPF always stores return value in R0, so we have to restore it. Fortunately, MRuby doesn't use R0, so we can just transpose it decisively. In the end, I generated the following BPF opcodes. To understand clearly, I colored these binaries. conclusion and demo. Now we can create a BPF binary object from Ruby scripts directly. Using this object and MRB and the BPF library, we will be able to compose all command binary. Writing a whole tool in Ruby will make programmers less context switches. I am planning to enable to share data structures definitions between the BPF and the user space program as one Ruby class, but it's under construction. Let's take a look at Rucy's demonstrations in action. At first, I'll show the C group demo. This is a target Ruby script. This can be compiled with Rucy command. The generated binary is a valid L format. Then, making a C group, load this object to the group. Now, process can access urandom, but assigning current process to the group, the urandom is not accessible. This is filter working. The next demo is about tracing kernel functions. These Rucy and MRB code will trace kernel's function called TCP connect. This is Rucy trace code. Checker section is different. And compile this into an object. This is BPF opcode generated by Rucy. Generate header skeleton. This is a generated skeleton of the BPF program. So embed this into MRB binary program and run this. Hitting curl command. Curl internally uses TCP connect and it is logged. Also using dirget. And then getting traced result. Also, SSH makes a TCP connect internally. Finally, I'm going to talk about restrictions and aimings at the future. I have only implemented the really minimum basic BPF functionality. For example, handling the BPF map data structure is unimplemented, and many features in real BPF can't be used in Rucy for now. I'd like to gradually implement these required features and create sample tools for real-world BPF operations. This is all about the story of Rucy. Thank you. ありがとうございました。